If you fell into Neptune right now, you wouldn't die by fire. You would be torn apart by wind. At the far edge of the solar system, nearly 4.5 billion kilometers from us, there exists a deep blue world where storms could swallow the entire Earth. A place where sunlight lingers only as a fading memory, where temperatures plunge to -214 degrees Celsius. Yet paradoxically, the planet radiates more energy than it receives. This is Neptune, the 8th planet, the final ice giant before the abyss of interstellar space. Neptune was not discovered by chance through a telescope. It was found through mathematics. In 1846, astronomers noticed that Uranus's orbit was slightly disturbed, as if an invisible force were tugging at it. Two mathematicians, Urbain Le Verrier and John Couch Adams, working independently in different countries, calculated the position of an unseen planet. When Johann Galle pointed his telescope to the predicted coordinates, Neptune appeared. For the first time in history, humanity discovered a world with intellect before seeing it with its eyes. Neptune has a diameter of about 49,244 kilometers, nearly 4 times that of Earth. Yet its mass is 17 times greater than our planets. It orbits the Sun once every 165 Earth years. That means since its discovery in 1846, it completed its first full orbit only in 2011. A single year on Neptune lasts longer than a human lifetime. Its iconic blue color is not from water. It comes from methane in the atmosphere, which absorbs red light and reflects blue wavelengths. But that blue is not gentle. Beneath the cloud tops lies a frozen inferno of hydrogen, helium, and methane compressed into supercritical fluid states. The pressure deep inside could crush any familiar form of matter. Models suggest that thousands of kilometers below the clouds, methane may be compressed so intensely that carbon separates and falls as diamonds. Diamond rain, not a myth. Laboratory experiments have recreated similar conditions and demonstrated that it is physically possible. Neptune's atmosphere hosts winds reaching up to 2,100 kilometers per hour, the fastest in the entire solar system. Speeds far beyond any storm ever recorded on Earth. More terrifying still, this happens on a planet receiving less than 1% of the sunlight that reaches us. In 1989, NASA's Voyager 2 spacecraft flew past Neptune. To this day, it remains the only spacecraft ever to visit the planet. The images it sent back stunned the world. On the atmosphere's surface appeared a massive dark spot, the Great Dark Spot, a storm roughly the size of Earth. Not long afterward, when the Hubble Space Telescope looked again, the Great Dark Spot had vanished. Yet new storms emerged. They are born, they migrate, they dissipate, and they reform. Neptune is never still. What puzzled scientists is this: how can a planet so far from the Sun possess such violent atmospheric activity? The answer lies within. Neptune emits about 2.6 times more energy than it receives from the Sun. A mysterious internal heat source is still active, possibly from gravitational contraction or leftover heat from its formation. Beneath the thick cloud layers lies an ocean unlike any other. Not ordinary liquid water, but a superheated mixture of water, ammonia, and methane under crushing pressure. Scientists call it hot ice, a contradiction that sounds like science fiction. Neptune's magnetic field is equally strange. It is tilted about 47 degrees relative to the planet's rotation axis and offset from its center. This creates complex magnetic fluctuations, bending radiation in chaotic patterns. Then there are the rings. Not as bright as Saturn's, but Neptune possesses a faint ring system composed of 5 main rings: Galle, Le Verrier, Lassell, Arago, and Adams. Within the Adams ring are dense arcs of material, rare formations where matter clumps into segments rather than spreading evenly. Orbiting this dark blue world are 14 known moons. The largest is Triton, a bizarre and fascinating world. Triton orbits in the opposite direction of Neptune's rotation, indicating it did not form alongside the planet but was captured from the Kuiper Belt. Its surface is covered in frozen nitrogen, with geyser-like plumes that erupt not water, but ice and frigid gas. Triton is slowly spiraling inward toward Neptune. In several billion years, tidal forces will tear it apart, forming a brilliant ring before it is ultimately consumed. Neptune is not just a planet. It is the gateway to the outer frontier of the solar system. Beyond it lies the Kuiper Belt, a vast region populated by millions of icy bodies, including Pluto. It represents the boundary between the familiar and primordial darkness. Scientists believe Neptune-like planets may be common throughout the galaxy. Many exoplanets discovered share similar sizes and masses. Understanding Neptune could unlock the secrets of thousands of distant worlds. And yet, paradoxically, we know very little about it. Since Voyager 2, no mission has returned. Proposals such as Neptune Odyssey remain on the drawing board, a colossal, violent, mysterious world left behind in the dark. Imagine one day a new probe plunging into its atmosphere, cameras transmitting images of colossal swirling clouds, lightning flashing through deep blue darkness, sensors recording sudden spikes in pressure before being crushed into silence. Neptune does not welcome visitors. It quietly orbits the Sun at the system's edge, completing one revolution every 165 years, while generations of humanity are born and fade like brief flashes. It witnesses Earth's transformations without ever knowing. A planet discovered by equation. A world with the fastest winds in the solar system. A place where diamonds may fall like rain. A moon awaiting its execution by gravity. And this is only the surface of that dark blue giant. The next chapter descends deeper into its interior structure, bold hypotheses about its core, its evolution across billions of years, and the possibility that it hides secrets capable of rewriting our understanding of planetary formation. The darkness beyond Neptune has never been silent. Beneath those frigid blue cloud layers is not empty space. It is a colossal engine that has been running silently for more than 4.5 billion years. Neptune is classified as an ice giant, unlike Jupiter and Saturn, which are gas giants. The difference is not in appearance, but in the deep internal structure. If you could slice this planet in half, you would not see a simple ball of gas, but a complex multi-layered world so intricate that every model remains partly hypothetical. The outermost layer is an atmosphere thousands of kilometers thick, dominated by hydrogen and helium, with methane making up only about 1 to 2%, yet enough to paint the entire planet its characteristic deep blue. Temperatures at the cloud tops can drop to minus 214 degrees Celsius, but the deeper you go, the hotter it becomes. Beneath the atmosphere lies the mantle, the layer that makes up most of the planet's volume. This is not molten rock like Earth's mantle. It is an ultra-dense ocean of water, ammonia, and methane existing in a supercritical fluid state. Pressure here reaches millions of times that of Earth's atmosphere. Temperatures may exceed 5,000 degrees Celsius. An ocean as hot as lava, yet compressed like metal. Under such conditions, molecules do not behave in familiar ways. Water does not boil. Methane does not evaporate. They are forced into exotic states of matter that laboratories on Earth can reproduce only for fractions of a second using extremely powerful lasers. Recent experiments suggest that under similar pressures, carbon within methane can crystallize into diamonds and fall like rain, not just a few glittering stones. Potentially diamond storms lasting millions of years, falling through the mantle and accumulating near the core. If that is true, a vast diamond layer could exist inside Neptune. Deeper still lies the core, the most mysterious region of all. Models estimate it has a mass about 1 to 1.5 times that of Earth, composed of rock and heavy metals. Yet no one knows its exact size, state, or structure. It may be solid. It may be compressed into something almost fluid. It may be slowly releasing heat, sustaining the fury seen at the surface. For decades, what has puzzled scientists most is Neptune's internal energy. The planet receives very little energy from the Sun, only about 1/900th of what Earth receives. At an average distance of 30 astronomical units, sunlight is merely a bright point in the sky, And yet Neptune radiates about 2.6 times more energy than it absorbs. Where does that energy come from? One hypothesis suggests it is leftover heat from formation, when matter collapsed under gravity, releasing enormous energy. Unlike neighboring Uranus, which has a similar structure but appears almost cold internally, Neptune seems to have retained a more active internal engine. Another hypothesis points to differences in convection. If Uranus's mantle is stably layered, trapping heat inside, Neptune may have stronger convective currents that allow heat to rise and stir the atmosphere. This internal heat could be the driving force behind its terrifying winds. Imagine a planet with no solid surface. You cannot stand on it. You can only fall. When Voyager 2 flew past in 1989, it recorded wind speeds reaching 2,100 kilometers per hour. At mid-latitudes, winds blow opposite the planet's rotation, forming atmospheric bands similar to Jupiter's, but far more violent. These massive storms form from the temperature contrast between the hot interior and the cold upper atmosphere. The Great Dark Spot observed by Voyager 2 was a gigantic vortex, similar to Jupiter's Great Red Spot. But unlike Jupiter, Neptune's storms do not last for centuries. They appear and disappear within a few years. The Hubble Space Telescope detected new dark spots in 1994, 2015, and 2018. Some storms drifted toward the equator before suddenly dissipating. Some vortices changed direction. Others seem to vanish without a trace. Neptune is the largest aerodynamic laboratory in the solar system. And there is something even more frightening: lightning. Atmospheric models and radio observations suggest lightning may exist within its deep clouds. But this is not water-based lightning like on Earth. It could be methane lightning, ammonia lightning, colossal electrical discharges cutting through hundreds of kilometers of dense atmosphere. Neptune's unusual magnetic field makes everything even more complex. It is tilted 47 degrees relative to the planet's rotation axis and offset from its center. This causes the magnetosphere to wobble like a distorted spinning top, generating powerful fluctuations as it interacts with the solar wind. Voyager 2 detected radiation pulses and asymmetric magnetic structures, suggesting that the magnetic field may not originate from a deep metallic core like Earth's. Instead, it could arise from a conductive mantle, where water and ammonia are compressed into a state known as supersonic water. Supersonic water is a state of matter in which hydrogen ions move freely through a fixed lattice of oxygen, behaving partly like a solid, partly like a liquid. Under such conditions, the material can conduct electricity efficiently, generating the strange magnetic field we observe. Neptune is not only strange in the present, it tells a story about the solar system's chaotic past. Orbital evolution models suggest that the giant planets may have shifted positions after their formation. Neptune may once have orbited closer to the Sun before being pushed outward during a chaotic phase of planetary scattering. This migration could have disrupted the Kuiper Belt, captured Triton, and shaped the outer architecture of the solar system. Triton, the largest moon, has a retrograde, nearly circular inclined orbit. This suggests it was once an independent body, perhaps similar to Pluto, captured by Neptune's gravity. That event must have created violent chaos in the original satellite system, possibly destroying several other moons. Today, Triton remains geologically active. Voyager 2 captured images of nitrogen geysers rising up to 8 kilometers high, leaving dark streaks across the icy surface. Its surface is relatively young, with few impact craters, indicating ongoing resurfacing. A subsurface ocean may exist beneath its thick icy crust. In a few billion years, tidal forces will draw Triton ever closer. Once it crosses the Roche limit, it will be torn apart, forming a brilliant ring before its fragments gradually spiral down into the planet. A celestial execution, already written into the future. Neptune is waiting, but we have not returned. More than 3 decades have passed since Voyager 2. Mission proposals such as Neptune Odyssey and Triton have been put forward to study its internal structure and Triton in greater detail. Yet enormous costs and extreme distance have repeatedly delayed them. Meanwhile, thousands of Neptune-like exoplanets have been discovered orbiting other stars. They represent one of the most common classes of planets in the galaxy. Understanding Neptune means understanding one of the universe's most widespread planetary types. And yet we have only brushed past it for a few brief hours in 1989. A colossal world of surging energy, diamond rain, oceans of burning ice, warped magnetic fields, and storms capable of swallowing entire planets. All of it spinning in frozen darkness. And beyond its orbit lies an abyss without light. If Neptune were to vanish tomorrow, the edge of the solar system would collapse in ways we can scarcely imagine. It is not just a planet, it is the final gravitational wall before the wild frontier of the Kuiper Belt, a region where millions of icy bodies drift in darkness. Its gravity shapes the orbits of countless smaller objects, maintaining a fragile order at the outer rim. Without Neptune, that structure would descend into chaos. The Kuiper Belt begins just beyond its orbit, stretching from about 30 to over 50 astronomical units from the Sun. Pluto is only one of its countless members. Many objects are locked in orbital resonance with Neptune, especially the 3-to-2 resonance, meaning for every 3 orbits they complete around the Sun, Neptune completes 2. That resonance keeps them from colliding. In Neptune is the invisible conductor of a frozen symphony. Dynamical models suggest that during the early history of the solar system, the giant planets may have migrated significantly. The NICE model, developed in France, proposes that Neptune once orbited closer to the Sun before gradually moving outward due to gravitational interactions with other planets and leftover disk material. As it migrated, it swept through the primordial Kuiper Belt, scattering some objects outward and capturing others into new orbits. That migration may have triggered the late heavy bombardment on Earth around 3.9 billion years ago, when countless asteroids and comets slammed into the inner planets. The craters on the Moon are the remaining evidence. A planet at the distant edge indirectly shaped Earth's geological history, though Neptune has never been passive in its role. Return to Triton, the strange retrograde moon. When it was captured, the gravitational energy released may have heated its interior, melting ice and forming a subsurface ocean. If that ocean still exists today, Triton becomes one of the potential candidates for microbial life beyond Earth. Triton's surface temperature is around -235 degrees Celsius, colder than any other world ever visited by a spacecraft. Yet, it remains active. Nitrogen geysers observed by Voyager 2 rose as high as 8 kilometers, leaving streaks hundreds of kilometers long across the surface. This spectacle unfolds nearly 4.5 billion kilometers from the Sun, a world colder than death, still breathing. Beyond Triton, Neptune has 13 other known moons. Nereid with its highly elongated orbit, Proteus, Larissa, Despina, Galatea. Many small, irregular, dark bodies that may be remnants of an earlier satellite system disrupted when Triton was captured. Neptune's faint ring system remains another mystery. The arcs within the atom's ring, named Liberté, Égalité, Fraternité, persist as dense clumps rather than spreading evenly as theory would predict. Gravitational interactions with the moon Galatea may stabilize them, but the detailed mechanism is still not fully understood. Each element of this system feels like a missing piece of a larger puzzle. Meanwhile, beyond our solar system, astronomers have discovered thousands of mini-Neptunes and warm Neptunes, planets between 2 and 20 times the mass of Earth, with thick atmospheres that may contain water or hydrogen. And data from the Kepler Space Telescope suggest that this class of planet is extremely common in our galaxy. The irony is striking. While we discover countless Neptunes hundreds of light years away, we understand so little about our own. Uranus and Neptune appear similar from a distance, yet internally they may be profoundly different. Uranus emits almost no significant internal heat. Neptune radiates energy intensely. Uranus is tilted 98 degrees, rotating almost on its side. Neptune is tilted about 28 degrees, more like Earth. Two sibling planets with opposite personalities. One hypothesis suggests Uranus experienced a massive impact that disrupted its internal structure and trapped its heat. Neptune may have avoided such a collision, preserving convective processes that allow heat to escape and fuel its supersonic storms. Small differences in the past may have created completely different destinies. Today, space agencies are seriously considering a return mission. NASA has proposed Neptune Odyssey, an orbiter carrying an atmospheric probe, potentially launching in the 2030s. The European Space Agency has studied similar concepts. The goal is not merely to capture beautiful images, but to drop a probe through the clouds to measure chemical composition, isotopic ratios, and thermal structure. Such a probe would survive only minutes before being crushed by increasing pressure. Yet the data collected could answer questions that have persisted for nearly 2 centuries. What exactly composes the core? How much water is truly present? How much methane? How does convection operate? Why is the magnetic field so offset? These questions are not simple curiosities. They are directly tied to how planets form. If we understand Neptune, we understand one of the most common types of planets in the universe. And from there, we better grasp the potential for life in other star systems. Imagine the day an orbiter finally slips into Neptune's orbit after a journey lasting more than a decade. High-resolution cameras capture newly forming storms, lightning flashing through deep blue darkness. A probe plunges downward through methane clouds, transmitting its final signal before silence. On Earth, scientists hold their breath. At that distance, radio signals take more than 4 hours to arrive. Every byte of data is a triumph. Neptune continues its slow rotation, one spin every 16 hours. A single year lasts 165 Earth years. Since its discovery in 1846, it completed its first full orbit only in 2011. It is now at the beginning of its second known revolution since humanity became aware of its existence. We have witnessed only a tiny fraction of its seasons. Climate models suggest seasonal changes may strongly influence storm activity. When one hemisphere receives more sunlight, cloud structures shift and dark spots appear more frequently. Yet with such a long orbital cycle, tracking these changes demands patience across generations. Neptune is a test of time. It reminds us that the universe does not revolve around human lifespans. It moves to rhythms measured in billions of years. Its storms form and dissipate while entire generations on Earth grow old and fade. At the outer frontier, where sunlight is faint, where temperatures freeze everything, while where winds outrun sound, there exists a deep blue planet, violent and silent at once. A world discovered by equation, a planet of diamond rain, a colossal heat engine in the dark, the guardian of the Kuiper Belt. Neptune does not need us to exist, but we need it to understand where we stand in the cosmic picture. And at the far edge of the solar system, between frozen darkness and blue tempests, Neptune keeps turning. No noise, no hurry, patiently waiting for humanity to return.